Hello, and welcome to my solar panel bracket design for this year's Mech4402 design project. This year's design project requires the redesign of solar panel mounting brackets. So the geometry is constrained in several different locations. There must be a 10 centimeter hole, which is 25 centimeters from the fastening location where the bracket will be welded to the solar panel. And that distance is 80 centimeters according to my student number. And the panel itself is 3.6 meters by 5.1 meters according to my student number, and it will be 2 meters off of the ground. So I've broken down the design challenge into various test cases that I will evaluate in CFD software StarCCM. So this slide kind of details the design process that I followed for this project. In phase 0, I made some assumptions based on the information given and did some preliminary calculations to get a head start and idea of what I was working with. Phase 1 was CFD analysis on the solar panel test cases for the previous slide, and this identifies basically the loading conditions. So I identified the case with the worst loading conditions, and then I used that for phase 2, which I did the FEM analysis of the baseline mounting bracket and identified areas to improve for the first design iteration. Phase 3, I improved the geometry based on the results from phase 2 and then ran the analysis again, identified areas to improve the design again for iteration 2. And phase 4, I made those changes from phase 3, ran the analysis again, and then predicted when the bracket would fail. So before I was able to conduct my CFD to actually extract values, I did a mesh independency test, and this was basically to evaluate how to identify basically the most efficient mesh with the least computational cost. So I refined the mesh after every simulation and then compared the values that were extracted from it. So the CFD analysis ran indicated that the 90-degree plate with the head-on winds yielded the worst loading conditions. And this is to be expected as this test case has the largest frontal area, which obscures the most wind from all the test cases. And this is evident by the large vortices you see here in the streamline plot. So for FEA analysis, the mesh independency test was also conducted, and again refining the mesh after every simulation to identify the most efficient mesh with the least computational costs, which also yielded the same sort of values. So here is the results from the baseline FEA. There's very little displacement and very little stress exhibited on this baseline model. The factor of safety of this model was 37.71, which is a very high factor of safety. So I figured that, since there is not a lot of stress exhibited in the bottom corners here and here, I was able to alleviate that for the first design iteration. So as you can see, I did delete some of this material here just to see how that would affect it. I think I also made this design thinner in terms of depth going into the page. And so this yielded a factor of safety of 25. So still very, very high factor of safety, which means that it's probably over-designed. So then my final iteration, I made this sort of sheet metal mounting bracket. And I kept that same sort of profile here, except I made this, I think, 1.5 centimeters thin, and I was able to sort of create a bend here in the sheet metal, which this piece attaches to the panel itself at the top. And this yielded a factor of safety of 6. So it's still sturdy, and it only has like 1 millimeter of deflection, displacement, which is still acceptable for this design. Iteration 2, like I mentioned, is made from 1.5 centimeters thick sheet metal with a bent flange that attaches to the panel. and it does have a factor of safety of 6. This design uses 81.43% less material than the baseline model, and these material savings will result in a cost reduction when manufacturing this product. So this is why this design was chosen for this project.